Our impeller design and testing activities provide some exposure to a handful of science and engineering concepts. The fountain pump we will be using in our fish tank model is actually an integrated design combining the electric motor used to drive the pump. The rotor, or rotating portion of the electrical motor, is combined with the impeller as one assembly. The fountain pump is an energy conversion device. This ability to convert energy provides a framework for our experiments and helps us define and characterize the performance in both flow rate and efficiency of the pump. This presentation will provide a basis in these topic areas: energy conversion, electrical energy and power, mechanical energy and power, flow rate and velocity, and finally system efficiency. As an energy conversion device, our fountain pumps operate in a manner consistent with most pumping systems. The motor applies electrical energy provided from the wall to create rotating magnetic fields. Those magnetic fields cause the magnet that is incorporated with the impeller to spin. The impeller and magnet have mass and now some rotational kinetic energy. The rotational kinetic energy now in the impeller assembly impacts the water when the pump is submerged. The water is moved and the kinetic energy of motion is added to the water. Additionally, the action of the water moving up to a higher level adds potential energy to the water. One final item: the action of pushing the water out through the discharge also creates some mechanical pressure within the water. This is also a form of potential energy. This will be ignored in our low pressure system, but could be more relevant in other systems. Our electrical measurements are simple during this portion of our class. We will come back to this in more detail later in the semester. Let's discuss some key ideas as an introduction and cover the measurements and calculations. When we discuss the topic of electricity, most people have an underlying familiarity. Centermost of these are the ideas of a battery or our household outlets as a source of electricity. Many might also mention concepts of voltage and current, and others might mention two other concepts: electron storage. You might rub your feet on the carpet to store charge so that you can shock your friends. You might use a Van de Graaff generator to capture quite a few electrons and get more energetic discharge. They might also discuss electron flow. Elementary, middle, and high school science classes have usually discussed how the flowing electrons move through flashlight bulbs or other items to produce sound or heat. These ideas are related to the differences between electrical energy and electrical power. Understanding the difference somewhat better will contribute to other discussions of energy throughout engineering. You won't become experts, but your team will gain some experience with measurement and calculation of both energy and power provided to the motor, in our case the fountain pump. Two measurements that are often needed and used for determining power and energy are those for voltage and current. First, the voltage of a source, whether it's a battery or an outlet, is an indication of the power supply's ability to push electrons through a circuit. The circuit components also influence the electron flow, but we'll investigate this more later. The units for voltage are volts. Our second item is the current flow from the source, which the battery or the outlet, is an indication of how fast the energy is being consumed by the circuit. The units for current are amperes. Our measurement equipment during this portion of our work is a digital electricity usage monitor used to check the power consumption of a household device. It provides the measurement for both voltage and current. As shown here, the display also shows power, but because it's intended to measure higher power items, it does not display a low power reading with the necessary significant digits. It will be necessary to use the voltage and current readings to get more precise results for our purposes. Power. The calculation is the result of the product of voltage and current. The resulting units are in joules per second, and as a rate of change shown by the units, it helps to see that the energy is provided and consumed at a periodic rate. Energy. To determine the total energy provided to the fountain pump, we need only measure how long the power is delivered to the pump. The product of power multiplied by the time in seconds quantifies how much energy in joules was consumed by the fountain pump. For an example, a pump that runs for 10 seconds while consuming 5 watts of electrical power used a total of 50 joules of energy. We'll repeat these measurements in class for our experiments. The phrase energy in the water might sound misleading. However, it is true that the fountain pump puts water in motion and can move the water to a higher position in comparison to the source of the water. The sketch here shows a pump that draws water from a tank and moves the water up a tube to an exit height where the water is discharged. The energy in the water has two forms: potential energy. The water that exits the tube has been raised to a height above the original tank level. The added energy is found by multiplying the mass of the water by the gravitational acceleration and the increase in height. Stated differently, the potential energy is mgh, mass times gravity times height. To highlight the available energy, imagine that you operated the pump for a period of time and filled a bucket resting at the new height. Now, if dropped, the available potential energy of the water in the bucket would be more obvious with the noise, damage to the bucket, and anything it might impact. Let's talk about the kinetic energy. The water that exits the tube also has some velocity or speed. As an object in motion, the water has kinetic energy of motion that is found by multiplying the mass times the square of the velocity and then dividing the product by 2. Stated differently, the kinetic energy is 1/2 mv squared. The total energy, the energy content of the water resulting from the pumping actions, is the sum of both the potential and kinetic energy. These equations are shown below the image on the right. The relationship between power and energy is the same for the mechanical applications as it is for electrical. Our testing will require that we record the time. This will allow conversion between total energy added to the water and the rate at which that energy is added as a measure of power. These calculations are connected to the test configuration and the concept of flow rate. A discussion of flow rate requires that we highlight the relationship between flow rate and the velocity of the water. This is a direct connection to the test configuration of the fountain pump and the tubing. In order to determine the kinetic energy added to the water, we must know the velocity of the water. Our experiment will require an indirect measurement and a calculation. Flow rate is defined as the change in volume over the change in time. A household example, a hose or sprinkler system, is often characterized by the flow rate, usually measured in gallons per minute. The flow rate can also be seen as proportional to the product of the area of the pipe and the velocity of the water passing through the pipe. This allows us to come back and find the velocity exiting the pipe. The image on the right shows a pipe with a uniform flow rate passing through the pipe. The pipe's change in area from left to right causes the water to travel through a smaller cross-sectional area and have a greater velocity in order to maintain the same flow rate. Spraying your friends with a hose highlights this. Without opening the valve further, covering the end of the hose with your thumb forces water to increase in velocity and shoot farther while the same volume is coming out of the faucet. Our experiment will require the application of these two equations to test the flow rates and determine the velocity of the water moved by our fountain pumps. System efficiency is presented in many contexts within science and engineering. When discussing energy, it is typically defined as a measure of how effectively a system uses energy provided to it. Mathematically, this is done by comparing the work, or energy, accomplished as a ratio to the energy provided to the system. Generally, it is presented as a percentage. Stated more directly, the efficiency is determined by dividing the output energy by the input energy and converting the resulting ratio to a percentage. For our system, we'll bring together the electrical energy provided to the pump as the input energy, the product of voltage, current, and time. The output energy is a combination of the potential and kinetic energy of the water as it leaves the elevated tubing. Mass times gravity times height, plus the kinetic energy at 1/2 mv squared. Our experiments will apply these concepts as we change the exit height of the tube and compare the results. The next portion of the video materials will demonstrate the experimental procedures you can expect to be completing during the laboratory.